AB3 monoprotic and polyprotic acids. We can always say an acid can donate 1 H for sure, but some acids will donate more than 1 H. They will be diprotic or polyprotic. Could be triprotic if they have 3 H's to donate. So I can see that HCl in this example here is only going to donate 1 H. It only has 1 H. HNO3 is the same, but what about H2SO4? Down here, H2SO4 has 2 H's that it probably could donate. Check on page 8 and 9 in your data booklet just to confirm this. You'll see that H2SO4 can donate 1 H and become HSO4, 1 minus. And then that HSO4, 1 minus, is also found in the acid column on page 8 and 9, and so it can also donate an H and become SO4, 2 minus. So this is definitely diprotic, or polyprotic. My pen's not working. What about huku? When I see COOH, that is a weak acid. That H could ionize. That H could come off. So in this case, and you can confirm it on page 8 and 9, that both this H and this other H, terminal and beginning H, will come off, and you're left with uku, 2 minus. So that's diprotic or polyprotic as well. What about HCOOH? That's a good one. When I check page 8 and 9, only this H comes off. This other one doesn't show up. HCOO 1 minus does not show up in the acid column. So it's not an acid after that. It's only monoprotic. What about CH3COOH? A general rule is that this OH is going to leave, but if you see CH3, these are nonpolar. This is a nonpolar part of the molecule. And remember that they are in water. They will not dissociate in water. So those H's rarely leave. But you can confirm that on page 8 and 9. This is monoprotic. H2PO4, you can check it's diprotic or polyprotic. NH4 can donate 1 H. So ammonium is an acid. A weak acid only can donate that 1 H. So it's mono. So bases can be polyprotic or monoprotic depending on how many H's they can accept. Monoprotic acids like monoprotic bases like HCO3 1 minus can only accept 1 H. Confirm that on page 8 and 9 of your data booklet. Polyprotic bases like 2 minus anions can accept 2 H's, or 3 minus anions can accept 3 H's. Those would definitely be polyprotic. Again, if I have to label these bases, I'm going to look on pages 8 and 9 to confirm that these substances can accept at least 1 H to be monoprotic. 1 negative pretty much tells me that I'm going to accept 1 H. So these are both mono. This one's 2 negative, so it's diprotic. This is 1 negative, it's mono. What about water? Water can only accept 1 H and become H3O, so it's definitely mono. Oops. What about SO3 2 minus? Di. What about OH negative? That can accept an H and become H2O, but it can accept one more H and become H3O. So I'd say that's diprotic, which it doesn't look like from here, so we'll talk more about that one. Reactions involving polyprotic and monoprotic acids and bases pretty much follow the same principles we've been using so far for Bronsted-Lowry. 1 proton at a time. But we can write when the statement includes continuously added, we can write more than 1 H getting donated by using two reactions. So in this case, if I was given all these substances, here's a statement, oxalic acid, weak acid, write it as is, and it is with an ionic substance, potassium hydroxide, dissociates 100%, and I have a strong base. Using pages 8 and 9, the strong base reacts with the strongest acid present, and notice that my acid is not continuously added. It says the base is continuously added. So I'm writing a net ionic equation where weak acids stay as is. I'm going to write a single arrow for now because what's happening is all of this weak acid is going to get finally used up by OH, only because they wrote continuously added here. So this acid's going to donate an H. You can take it off the front or the back, or just double check page 8 and 9 if you feel more comfortable. And we're also going to get water. This is just going to keep running until this reaction can't go anymore. You could write a double arrow and state some reactant is present, but basically we're just going to have two products. Now we're going to add some more OH. It's continuously added. So now in my new situation, this is my newest acid that's present, and OH is still present. So I'm going to write my second reaction where I can donate my second my second proton. Okay, 1 minus AQ, and more OH is getting added. So we're going to get very similar results here. We're going to get, this time, a polyprotic base is formed, and water. Could I write an overall reaction for this? I could. I could write a net reaction that occurs. Remember the rules of Hess's law? That if something on the left is present and it's identical to something on the right, they can cancel each other out. So I'm going to look here and I see that this substance is exactly the same as that substance. These don't cancel each other out. These OHs accumulate. I have two OH here. And you can put double arrows, but let's just put a single one for now. This is the only time I see this, so it comes down. Two waters are formed. Is this going to balance? It should. My other reactant was the original acid. Didn't dissociate. There's my overall reaction. How do I double check that this is balanced? The negative charge of 2 on the left is equal to 2 negative on the right. Okay, this next page, let's see if I can get it going here. How about acid-base strength? You can use pages 8 and 9 to determine the strength, the relative strength of acids and bases, and that's what you could be asked. So you can look up different acids in the acid column there and compare them. But could two different acids that have the same concentration have the same number of hydronium ions in solution? What if you had a weak acid? What if you had CH3COOH and a strong acid? This is going to dissociate 100%, strong acids do, and I'll have H3O present. None of this HCl is left over time, and it's just H3O plus and Cl minus. This acid-base reaction is in equilibrium, so I'm always going to have some reactant and some product. You're not required to indicate what percent, but you could state that it's less than 50% by using page 8 and 9 to determine your acid and your base. But in this case, I'm not going to have as many hydronium ions floating around, so the concentration of just hydronium ions shows that this is not a very strong acid, just from looking at these two illustrations. So when we deal with weak acids, we're going to have to use our K value from page 8 and 9. Page 8 and 9 has the K values. When we talk about the top 6 acids, assume they ionize 100%, and whatever this concentration was, the original acid concentration, all of it becomes H3O plus. So if I asked you for pH here, you could find it. What's the pH of this? This substance is 1 mole per liter of H3O, and that's what I'm looking for. I'm looking for the negative log of H3O concentration. And if I fill that in with 1, I can find the pH. I can't do that here unless I know the H3O concentration. So that would either have to be given, but in many cases it won't be given. We'll only be given the original acid concentration. So we're going to use Ka and the equilibrium expression, products over reactants, to help figure out the pH, but first the H3O concentration. So I'm just going to move this page up. So Ka values are on page 8 and 9 for weak acids. Just a note, if you were comparing Ka values, you could determine the strength of the acids. So which of these acids is the strongest based on its Ka value? Remember that K is product concentration divided by reactant concentration. So if I have lots of product, then K is large. Which is the largest K value here, or the largest product? Looks like this one is, right? That's the largest. So I'm going to say from strongest to weakest is this trichloroacetic acid, and the weakest one is going to be one of these two large negative exponents. So here I've got 1.5. What's bigger, 1.5 or 1.4? 1.4 is smaller, so it's the smallest value. That would be my weakest acid, right? Then salicylic acid is your next strongest, and then I can use that glycolic acid.